we talk about isoelectric focusing, the basics, we have done this already a couple of months ago, but today we look at the method from a little bit different aspects to cover the entire picture. So on the front page you see already a schematic drawing how isoelectric focusing is working, and I will explain that a little bit better in detail. And on the right you see a result, very beautiful result of an isoelectric focusing analysis. Isoelectric focusing is a method which drives the molecules to their isoelectric points, so naturally can only be applied to samples which are amphoteric, which have an amphoteric character. And you know that proteins, peptides, also some dyes, anthocyans for instance, are amphoteric, so they have buffering groups, basic and acidic buffering groups. And here in this schematic drawing, you may know that already, when you put such a amphoteric molecule into a basic environment, you will get deprotonation of the carboxylic groups, so the molecule will have negative net charges. And if you put it into an acidic environment, it will be protonated, and then the amino groups will be protonated, which means the molecule has positive net charge. And naturally, there must, in between negative and positive net charges, there must be one situation where the negative and positive charges are the same, so the molecule becomes neutral and has a net charge of 0. And this is called the isoelectric point, which is very, very characteristic for each molecule. So each protein, for instance, has really a different isoelectric point from another one. There is a second thing which you should always bear in mind. Also, the net charge curve of each protein is very individually shaped. So when you plot the net charges over the pHs, over a pH scale, you will get very typical shape of the net charge curve, where the intersection with the x-axis is the isoelectric point. And this is another characteristicum of a protein, so you can describe a protein also via its net charge curve, and a net charge curve of a protein can really give you very important information about its behavior in some physicochemical situations. We have explained last time how you can make a titration curve analysis, so how you can determine such a net charge curve for your protein. If you look into the archive of SERVA, you find the old presentation, and there I have explained how titration curves can be done. Yes, so let me bring it to the point again. Isoelectric focusing is an electrophoretic separation of amphoteric substances within a pH gradient, and they are separated according to their isoelectric point. So the principle of electrophoresis in general is very simple to understand. A charged molecule, charged particle, is moving in an electric field. So if it is negatively charged, it will be attracted by the anode and move towards the anode. You can do this in a gel matrix or in a liquid phase. And as the mobility of the different molecules are different, depending on the size, on the charges and other properties, you will get the separation, because the speed of the molecule in the electric field is different depending on the electrophoretic mobility. And the speed is also dependent on the electric field strength. So the higher the electric field strength, which is measured in watt per centimeter, the faster is the migration of a molecule. But this field strength is, of course, also has an influence on all the molecules the same way. Yeah. So the isoelectric focusing has a special feature. It is done in a pH gradient. Whereas in zone electrophoresis you have a buffer system and you need buffer compartments to maintain a stable pH during the separation and stable buffering capacity of the system. In isoelectric focusing, you do not need electrode compartments. So you are preparing a pH gradient. I explain how this is done a little bit later. And you lock the pH gradient between the anode and the cathode of the system, so you don't need electrode compartments in general. It is a little bit different when you use special apparatus like a vertical apparatus. In isoelectric focusing, theoretically, you can apply a sample mixtures wherever you want within the pH gradient, theoretically I must say. I come to the practical aspects a little bit later. If you apply it like here in a pH gradient close to pH 6, part of the proteins will be positively charged, the basic ones, and the others will be negatively charged, the ones with the more carboxylic groups. And that means in the electric field, the positively charged migrate towards the cathode, the negatively charged the anode, and they approach the isoelectric point. When they arrive at the isoelectric point, they become uncharged because, yeah, as the definition is, and then they stay there, they stop. And so they are driven to the isoelectric point. But isoelectric focusing is preferably done in media which do not have a strong sieving effect. We don't want to have a sieving effect in isoelectric focusing because we only want to separate according to the charge. So usually you use liquid or gel with large pore sizes, which means that when a protein has arrived at its isoelectric point, it will not always stay there. It can diffuse away very quickly, but the system works against the diffusion. This is the so-called focusing effect, and that's why it's called focusing, because when a protein moves away from its isoelectric point, it will pick up a charge immediately, which is responsible that the molecule will migrate again back to the isoelectric point. Yeah, because the electrophoretic mobility is very low close to the isoelectric point, because there are only very, very low charges, we need a very high electric field strength, very high volt per centimeter, and in the end that means a very high voltage to drive the proteins through the isoelectric points and focus them. And that means in isoelectric focusing it's very important that we have power supplies which deliver more than 2,000 to 3,000 watts. This is different from normal zonal electrophoresis. So how is a pH gradient generated? So the first method which has been introduced, it was in 1966, practically, of last century. It was first time practically possible to separate proteins in a pH gradient. The invention was made by a Swedish man, Olof Westerberg, comes from Stockholm, and he has managed to synthesize a mixture of amphoteric buffers. They are called the Carrier Ampholytes, and I show here the name SERVA. In the history, so the first molecules which have been designed and synthesized in 1966 were called the ampholytes by a company called LKB. LKB is no longer existing, and also the reagents ampholytes are no longer on the market. But the company SERVA was indeed the second company who developed and produced Carrier Ampholytes, which are called the SERVA-lites. So you see that SERVA has quite a history in this area, and that was done in the beginning of the 70s of last century. So what are the features of these mixtures of buffers? These are molecules, amphoteric buffers, which have a very high buffering capacity at their own isoelectric point. This is very important, and that is the reason why it's necessary to synthesize them. You cannot use naturally existing amino acids or peptides for this. You have to make them by synthesis. And it should be a mixture of a few hundred. Usually they are between 600, 700, 800 different homologs, and the distribution of them should be even between pH 3 and, say, pH 10. So the concentration and the buffer capacity of them should be evenly distributed over the entire pH range. And another feature, they should not be too large. The molecules should not be larger than 1,000 Daltons. And so this mixture of amphoteric buffers is used in a gel or in a capillary or a liquid column. And so how do you generate a pH gradient out of this? Now, when you have them in a mixture, the basic individuals which have more amino groups will naturally become positively charged, because the average pH, the mean pH, will be about pH 7. So you will have protonated basic groups in the very basic molecules, and you will have deprotonated carboxylic groups in the acidic individuals. That means when you apply an electric field, the positively charged, the more basic ones, will migrate towards the cathode, and the negatively charged, the more acidic ones, will migrate towards the anode. And because they have a high buffering capacity at their own isoelectric point, they will buffer each against the other and will form a quite stable pH gradient between the extremes 3 and 10. You see that in the animation. I've tried to show that using colors. Now, in the beginning, isoelectric focusing was a preparative and not an analytical method. And on the left, you see a very old picture, the sucrose density gradient column, where the first isoelectric focusing experiments have been done. The sucrose density is used in order to stabilize the separated protein zones. So you fill them with water, and with about 2% of the Carrier Ampholytes, and apply the electric field and apply the sample. First the sample and then the electric field. The proteins will migrate to their isoelectric points. When the separation is finished, you can elute the column and can run the elution via a monitor, UV monitor for instance, to get the proteins recorded, and you collect the different samples in a sample collector, and so you have them as a preparative and an analytical result in the same time. But you can do, so it's almost not done anymore nowadays. Nowadays people do, for instance, capillary isoelectric focusing or free flow electrophoresis. These are separation techniques which do not use a gel matrix. And as I said, in isoelectric focusing, you don't want to have a sieving effect, and you have this so-called focusing effect. So it's a very useful technique to be done in liquid, like a liquid buffer film in free flow electrophoresis, where you apply the sample on one point, and the proteins differently charged will have different aberrations depending on the charge towards the cathode or the anode. And when they have passed these cuvette, the same sample type will always arrive at the same position. That will be collected by 96 tubing, and so you have a preparative and analytical technique here. In a capillary electrophoresis, is very easy to understand. You run them in an open capillary. These techniques are quite fast, and here you can separate quite a high amount of samples. So this can be done within a minute, for instance. But most people, and that was the first development after the column, already in the beginning of the 70s of last century, people started to use isoelectric focusing, apply isoelectric focusing in gels, mainly polyacrylamide gels. I will come back to agarose gels for a moment a little bit later. When I started working with isoelectric focusing, it was quite long ago, 1975, we had just such an instrument, which was a vertical system, as you see, with tubes, glass tubes, and you had to polymerize the polyacrylamide gels and insert the tubes into the system. You had, for instance, the cathodal solution, a base diluted alkaline solution at the top, and the acidic solution, diluted acid at the bottom. These were the electrodes, and you perform the separations within these tubes. Soon people also started to use slab gels, vertical slab gels with upper buffer, lower buffer. Here sample wells, run them from top to the bottom, or this is a system with a little bit better cooling than this one. And so the electrode solutions used here were mainly used as a buffer sink, as a temperature sink, and to avoid that the Carrier Ampholytes move out of the gel. But the major stream of isoelectric focusing methodology was going into the horizontal gels. And there was very soon, when after the first polyacrylamide gels were used for isoelectric focusing, was a chamber put on the market which is called the Multifor, that was coming from this company LKB, and still on the market since beginning of the 1970s. And the Multifor has a cooling plate where you have a water circulator, temperature circulator, pump cooled water through the cooling plate, so you have direct cooling of the gels. Formerly, the gels were polymerized on glass plates, but it's much more practical to polymerize them on plastic film material, so nowadays you run them on film support. And you can do this in very thin gels. When the gels in the 70s were like 2 millimeter thick, nowadays people perform isoelectric focusing in 0.5 millimeter or 0.6 millimeter, or even thinner layers of polyacrylamide. You can also apply the sample with filter paper or with other silicone stuff with little holes in it, with a silicone band with holes in it to apply the sample. Or it is also possible to polymerize little sample wells into the surface of the gel, but not going all through the layer, only about 1/3 of the layer, where you can pipette your samples. This is mainly done when you know already at which position in the pH gradient the sample has to be applied. I will come back to this matter a little bit later also. Some of the gels have such a good buffering capacity that you don't need filter paper strips. You just can place the electrode, like these are usually platinum wires, directly on the surface to make the contact with the electric field. But some gels require filter paper strips, which are soaked at the anode with a diluted acid and the cathode with a diluted base, or basic Carrier Ampholytes. Particularly, this is also necessary when you have high urea concentration on the gel, to lock in the pH gradient, so the Carrier Ampholytes will not leave the gel during focusing. And the isoelectric focusing in the fast system is always done without filter paper strips. This is a system from the company Pharmacia. Yeah, I said mostly people are using polyacrylamide, but you can also use agarose. So the people were also using agarose for isoelectric focusing, because the agarose has a few benefits. It's a completely non-toxic medium. Because it's a natural medium, and it produces very large pore sizes. So a 1% agarose gel has 115 nanometer pore size diameter, which is very beneficial for isoelectric focusing because you have no sieving effect at all. But I will soon tell you why people mostly prefer polyacrylamide gels. So here you have to make a chemical polymerization out of acrylamide and methylene bisacrylamide as a cross-linker. you start this polymerization with TNAD and ammonium persulfate, and then you get a three-dimensional network, and with a defined total acrylamide concentration, like usually 5% T, and a defined cross-linking factor of 3. This is the relative amount of cross-linker to the total acrylamide and cross-linking amount. Polyacrylamide gels are absolutely inert. They are completely transparent, very relatively flexible, which is not the case in agarose, but they have smaller pore sizes. As you see, like 5% T gel has only 5 nanometers compared to 150 nanometers. So why do people use mostly polyacrylamide gels? This comes mainly from a fact which is called electroendosmosis. So on the left you see electrophoretic migrations of charged molecules through a gel matrix, agarose, or polyacrylamide. But on the right you see an effect which is called the electroendosmosis, and it comes when charged groups are fixed on the surface of glass, for instance, and in the matrix. Now, agarose is a natural product coming from agar-agar, and there are still sulfonic and carboxylic groups in the matrix which cannot completely be removed. And in electrophoresis and in the basic part of isoelectric focusing, they will be deprotonated, and that means we have fixed negative charged groups on the glass surface and in the gel. And this is very bad because these negative charged groups will be attracted by the anode, and as they cannot move because they are fixed in the matrix, you will get a counter-reaction, which is a water transport, protonated water into the opposite direction, into the cathode direction. And this can be very dramatic. In agarose gels, you can have it can happen that the cathode will, after some time, be completely soaked with water, and the anode will be completely dry. So you have to do something. Very expensive agarose on the market. You have the positive charges to balance out the negative charges, and but it's never 100% electroendosmosis free. But polyacrylamide gels, when they're made with good acrylamide monomers, with no acrylic acids inside, they don't show this electroendosmosis effect, at least not very high effect. You can add some stuff to the gels. For instance, to the agarose gels, people were always adding some sorbitol to have higher viscosity in the gel and to keep the water back from the electroendosmosis, or monoethylene glycol, or both as a mixture to increase the viscosity. Sometimes people use urea in the gels for creating denaturing conditions, increase protein solubility, avoid aggregation and complex building of proteins. But urea you can only use in polyacrylamide gels. That's another point why polyacrylamide gels are usually preferred. You can add Zwitter ionic detergents also to increase protein solubility to the sample and to the gel. Non-ionic detergents have been used in the past, but they're not preferred anymore because they heavily interfere with mass spec analysis, and very often mass spec analysis is done later on downstream after the separation. You can also add separator molecules. Here's an example, for instance, the amino acid beta-alanine for the separation of the glycosylated hemoglobin A1C from non-glycosylated hemoglobin. This has been done a lot in the past for diagnosis of people who have diabetes or who are suspected to have diabetes. So the beta-alanine at a temperature of 15 degrees spreads out the pH gradient between pH 7.1 and pH 7.3, so you get a better resolution, particularly in this area where the two bands are. You can also add organic solvents. Up to 50% dimethyl sulfoxide can be added, for instance, if you need to do cryo isoelectric focusing for separating temperature-sensitive enzymes, for instance, in order to avoid freezing of the gel. That works quite nicely. Yeah, you can make the gels yourself. So the company SERVA offers the SERVA lights, the acrylamide and bis monomer solutions. So you don't need to weigh in acrylamide. Of course, you can also purchase powder from SERVA. And you know that acrylamide and bis are quite toxic components. You should avoid any contact with it as much as possible. The TMET and the ammonium persulfate is needed for initialization of the chain reaction for generating a gel, and yeah, urea sometimes is needed, as I said. You also can get the film support material where you can bind covalently the polyacrylamide gel to it. You can also have equipment. You can also make vertical gels if you prefer, if you want. Before we talk about benefits and disadvantages of horizontal or versus vertical gels, just want to mention the important parameters for isoelectric focusing. So I haven't mentioned that already. Sieving is not wanted, so you need large pore sizes usually. You need high voltage because the charge of the molecules close to the PI is very low. I have mentioned that already. Another thing is important to know: the isoelectric points of the Carrier Ampholytes as well as the sample proteins or peptides are highly dependent on the temperature. And also in these pH gradients some hotspots can develop where the temperature has to be removed. So it's very important to run isoelectric focusing at a defined temperature. Often it is 10 degrees when it's a native separation. And the sample application, in many cases under native conditions, it is very important to find out the optimal pH position to apply the mix of the proteins. And so you do in a horizontal system. That's very easy because you have an open surface and you can find by a test where you apply preferably your samples. And if you need denaturing conditions, you can also add urea to the gel matrix either by polymerizing that in, but then the gels are not very long stable, or you can pre-polymerize gels without urea because a urea solution is not very stable, and you can equilibrate or even better rehydrate gel, a dry gel in urea solution to get the urea into the matrix. How can you determine isoelectric points of proteins and identify more or less the proteins? Or yeah, identification is a little bit problematic, but very often you can do that. Yeah, there are marker protein mixtures with characteristic isoelectric points, with known isoelectric points. Highly purified proteins are mixed together, and that works very well for native conditions. So you can interpolate the pH, the isoelectric point of your samples. That does not work in, unfortunately, that does not work well or at all in urea conditions, because urea is modifying the isoelectric points, the conformations of the proteins, and is also splitting up some quaternary structures. So that is a little bit more problematic with urea. So what are the benefits of isoelectric focusing? There are a number of them. You can directly measure isoelectric points after the separation, particularly under native conditions, as I said. You get a very high resolution because of these focusing effects, these very sharp bands. You can apply native conditions and can determine enzymes with a seismogram technique. I will show you an example a little bit later on that. So it is a biological reaction still done after isoelectric focusing. Running the gels is very simple, very easy on these horizontal gel layers because there are no leakages of buffers and so on. It's very easy to apply. You can do preparative applications. You can load quite a lot of proteins on such a isoelectric focusing gel, and because the separation is performed just due to one isolated physicochemical parameter, the charge, the isoelectric points, it's an ideal method for combining it with a second method which separates only according to the size. So you have ideal conditions for two-dimensional electrophoresis for a very high resolution of a protein mixture. So what are the advantages of horizontal isoelectric focusing gels? Here you see sample wells or paper pieces which are placed on the gel. So first of all, the gels are film-backed. I said that you prefer soft gels with large pore sizes. That means that the mechanical stability of the gels is not very high. So that's the reason why you want to put them covalently on a film support. And also the separation works better the thinner the gel, the higher is the resolution. And also this means that you need a mechanical stabilization, which can easily be done for horizontal gels, not so easy for vertical. You can apply high voltages because you have no buffer tanks. You can apply the electrodes directly, so it's a safe system. You run them directly on a cooling plate, so now you can get very exact temperature control. You can choose your sample application position because you have an open surface, and you can rehydrate such gels which are on a film support easily with a urea solution. But there are also people who run vertical isoelectric focusing, also in ready-made gels, and all these benefits are not valuable here, but here the equipment costs much less money, is much easier. You cannot cool them very effectively. That means you don't need a cooling machine, so the equipment is cheaper, but you do not have all these benefits. But in some cases it's not necessary. The results in some cases are good enough in a small vertical isoelectric focusing gels. There is one point to mention that Carrier Ampholyte isoelectric focusing can have some troubles, namely the so-called cathodal drift. Here I show that with hemolysate, hemoglobin. So this is a colored molecule. You don't need to stain the proteins after separation. Here you see after 60 minutes the hemoglobin bands have nicely separated. But when you continue to do that, the basic, and this is pH 7.1 about here. So the gradient starts to drift. If you do a longer separation, you would need a longer separation for larger molecules, or when you have urea in the gel. And then you have one problem, that the basic part of the gradients is leaving the gel after some time, and also a little part of the acidic gradient will leave, and so you call that also plateau phenomenon, because the gradient starts to become flatter and flatter in the center and steeper at the two ends. This was the reason why in the 70s last century the immobilized pH gradients have been developed, an alternative where the pH gradient is generated by a gradient maker, and you are attaching carboxylic and tertiary amino groups during polymerization of the gel by using acrylamide derivatives with carboxylic and tertiary amino groups in special mixtures. And now the pH gradient is fixed to the matrix and cannot move anymore. This is mainly done under for 2D electrophoresis under the nature and conditions, because under native conditions immobilized pH gradients are a little bit problematic. If you want to know more about this, we can discuss that during discussion. Usually each sample is separated in individual strip, 3 mm wide, 0.5 mm thick. They are all on film support, and the company SERVA is offering 7 to 24 centimeter long strips, big variety, and also different gradients, linear, non-linear gradients, wide gradients, and short intervals for optimal separations. So a lot of different gels which have different thicknesses, different gradients on film support, or vertical gels are available from SERVA. Also rehydratable gels if you need, and the strips for the immobilized pH gradients, the IPG strips, are also available from SERVA. Here just a few points on the separation system. This is the little small blue vertical chamber for the vertical gels, and here you need liquid anodal and cathodal solution, a few hundred milliliters, and you cannot directly cool them in order to keep the pH gradient in the gel. It's not ideal, but for many applications we know it's quite useful, and there are papers around which explain that this separation is by far very good for some special applications. And here you see an example of a result of such a gel. You can also ask for a starter kit if you want to try that, and even the running buffer kit, all available. But the non plus ultra, the best you can do is run them horizontally. And I talked about the old multifold chamber, which is on the market more than 40 years already. And a lot of experiences have been collected, and finally a new system has been developed where you have a drawer. This is the cooling plate. You have an electrode lid which is placed on the gel, which has also a parking position there, so you can save a lot of space just putting the power supply on top of it. You can also make stacks of chambers, so you the old systems needed a lot of space because they had different lids which had to be placed somewhere on the lab bench. And what you do not see on the picture here, this is connected to a thermostatic circulator for having exact temperature. Here you see the electrode lid, that's the cathode, that's the anode, and what we use, what you don't see on the holder here, we are using platinated titanium rods for absolutely perfect electrode contact, and here's the aluminum oxide cooling plates. You see that some, like the precoats, are run with electrode strips. The focus gels are a little bit thicker, have a higher buffering capacity, and so you can also buy them with some sample wells, and here you apply the electrode directly on the surface. If you do not know where is the optimal sample application position, you can do this in a step dryer test with filter papers, for instance, very simply, and then keep the position always. Here you see the sample application into the little sample wells in such a horizontal gel. Few results. Here that's done in food analysis, stain gel, where the percentage of pork meat in beef can be measured by densitometry, scanning special bands, and quantitating the intensity of these bands. Gel rehydration can be done in such a tray within 1 hour on an orbital shaker very easily. This is done with dry gels, and here you have the Carrier Ampholytes in urea solution. Few words on the protein detection. So cyanograms are done by submitting the gel to a buffered substrate solution after the separation at a defined temperature, and coupling the enzyme substrate reaction later on with a dye, with a salt dye. I will show you in a moment a result of this. So that can be done after isoelectric focusing. If you want to see all the proteins, then you need to fix the proteins with 3-chloroacetic acid in order to get rid of the Carrier Ampholytes, but you fix the protein bands in the gel, because the Carrier Ampholytes should be removed because they would stain. They look a little bit, the molecules look a little bit like peptides, so they can stain with the typical staining reagents. The best staining, if it should be something like Kumasi staining, is SERVA Violet 17 for isoelectric focusing. And the best silver staining method is an ammoniacal silver staining, and both of these can be available from SERVA. So we have ready staining kits which take a lot of work away and give you good reproducibility. And if you need to do Western blotting, we have seen that it works best with pressure blotting, better than with electrophoretic blotting, because here you have to transfer proteins which are neutral, which do not have a net charge. And you can do this with pressure because the gel pore size is rather large, and you can move the proteins like capillary suction onto the surface of the blotting membrane. Here you see zymograms. I've collected those from the internet. You see acidic phosphatase, esterase. So here you specifically see only the enzymes at their isoelectric points which have done a substrate reaction and coupled with a diazo dye. Mostly these are diazo dye reactions like fast blue B, and you get this very specific pattern. A lot of plant geneticists and plant controllers are using that, but they also have done this for animal differentiation and so on. Here you see a chromatin staining. Of course, you can also use chromatin staining. These are potato proteins, so these are all the potato proteins in each lane of each potato variety. And here you see a result with a very sensitive ammoniacal silver staining, which is done a lot when you need very, very sensitive detection, like when cerebrospinal fluid has to be separated next to the serum of a patient to detect specific diseases, brain diseases or multiple sclerosis, done in routine analysis. Yeah, that was it. A little bit longer than usually. Sorry, there are so many slides. Thank you for your attention, and I'm open for questions.